So hello everyone, this is lecture 43 for the classical physics. In the last lecture we were discussing about the moment of inertia tensor, and I told you what is moment of inertia tensor, what it denotes. It represents actually the distribution of mass along the x, y and z axis. Okay, so you get this kind of matrix and that is called the moment of inertia tensor. And here if you have the symmetrical distribution around the x, y, z axis, then these of diagonal elements that we call product of inertia terms x, y, x, z, y, z, y, x, z, x, z, y all become 0 when there is a symmetrical distribution around x, y, z. Otherwise you will get the terms here also, and this complete tensor will give you all information about the mass distribution. And when you find the diagonalization matrix for this, or you diagonalize this and find the eigenvalues, so that give you for any particular structure the three principal axes around which the mass will be symmetrically distributed. So you can find the eigenvalues for a matrix, and eigenvectors will give you direction corresponding to those eigenvalues for the axis. So I told you what is kinetic energy, torque. Now let's see some questions based on all these concepts we discussed, because that is the main thing we need. That is a question solving problem solving thing. So this figure is given. This is xy axis and this mass is distributed this way. 2m here, coordinate is a0, 3m mass is here, aa minus aa, this for 4m, and m is minus a0. Now we need to find the moment of inertia tensor for the system of masses. So we need to moment of inertia tensor for this. We need to find this. So let's do this first. So what we need is Ixx, means all these terms we require. This is your moment of inertia tensor. We need all these terms, and we already discussed the formula. For xy, it will be equal to yx, and formula is mi xi yi. And for z, it will be xi zi, yz will be yi zi. So first let's find for the z terms, because we know these all four masses lying in the xy plane. So z component will be 0. So Ixz, Izx, Iyz, Izy will be equal to 0 always, because there is no component on the z will be 0. So that will give you 0. But for Ixy, Yx, it will be mi xi yi. So we'll take all the sums for all the masses. So first it is for the this one, this m has the coordinate minus a, and y component is 0, so it will give you 0. Then 2m a 0 will give you 0, and the multiply of 2m 4m multiply minus a will give you 4m a square minus 4m a square, and this will give you 3m a into a square. So total sum will be 4 minus, this is minus 4m, this is plus 3m, it will give you minus outside 3m a square minus 4m a square, and minus m a square will result to plus m a square, because this minus is also extra. So you just need to find the sum of all the masses. So for all the masses, find xy coordinates, multiply them and take the mass. So just take the sum of all of them, it will give you this, because these two will give you 0, because y component is 0 here. So when you put the y0, it will give you 0. So only two masses will give you, that is 3m and 4m. So this is your ixy or yx. So you have these four terms, you have ix, yx. Now you have 6 terms already, you need 3 more terms, that is Ixx, Iyy, Izz. So formula for Ixx is nothing but mi square plus zi square. So we will take the sum again. So for all the 4 particles, zi is 0 and yi is 0 for these two masses. So we need to take only for these two. So it will be 4m multiply x square and 3m multiply x square. So it will give you 7. 3m square, 4m square will give you 7m square. Then Iyy formula will be xi square plus zi square. Now zi is 0. So we need to take xi for those, means xi exists for all the 4. So it is existing for all the 4. It will be m a square, 2m a square, 3m a square, 4m a square. It will be 4, 3, 7, 8, 9, 10. It will be 10m a square. Now for Izz, formula will be this. Now xy exists for all the 4 particles. So take the corresponding coordinates and take the masses. For m, it will be minus a square 0 square, 2m a square 0 square, 3m a square, 4m a square. It will give you here 8m a square. It will give you 6m a square. This will give you m a square. This will give you 2m a square. So it will be 6, 8, 14 and 3. 2 plus 1, 3 will give you 17m a square. Now you have all these 3 terms and all the 6 terms. So you have all the complete 9 terms. You can write the momentum inertia tensor. That will be this. Now this was our first question, so we already find it the momentum inertia tensor. Now second question is, find the angular momentum if the system is rotated with this. So the axis is given and we need to find the angular momentum. We know L is nothing but I tensor omega. So this is the formula. So just write this momentum inertia tensor here, and omega is given already, and find the value of L, means just multiply these two matrices. This will be this. Now take the ma square omega common, it will give you 1 tan 0. So this can give you direction because this is vector, it is I cap tan j cap and ma square omega. So this will be your angular momentum. Now there is one more question. Calculate the moment of inertia about the axis. So particular axis is given and we need to find the moment of inertia. So before solving this, write these 2 points. Because here you can see that we are getting direction for angular momentum is x cap y cap. And direction for omega was only omega y cap. So see here we don't have the same direction for angular velocity and angular momentum. But when we are doing the symmetrical axes and the momentum inertia we are finding, there we are getting the same direction for omega and L. So it is not always true that they should be in the same direction. So that is a general case, means they should not be equal in general. So if mass distribution about xyz axis is not symmetrical in rotation, then omega will not be parallel to L in general. It can be equal, but in general it is not equal. Okay. Only if we rotate the system about the principal axis, the omega and L will be parallel. So this we proved already when we discussed all the symmetrical axes. So there we proved that omega and L have the same direction. Now there is this third question. We need to find the moment of inertia about this axis. So I already give you this formula. Around any axis you can find moment of inertia will be transpose of that axis and that xa and x transpose a xa. This is nothing but if you have xa in the column vector, take the transpose and you have already moment of inertia tensor and again transpose and that vector. So just multiply these, put the whole values and you can find the moment of inertia. So it is along this, we need to find along this. So transpose will be 0 1 0 and 0 1 0. Moment of inertia tensor will be this, we already find this. Now 0 1 0 0 1 0. After solving this, we will get 10 ma square. So this will be your moment of inertia along this axis. Now there is one more question. So these 3 figures are given and we need to find that, let me show you this question, what we need to find. The figure shows the thin square sheets of metal of uniform density along with possible choices for a set of principal axes of moment of inertia lying in the plane of sheet. The correct choices for the principal axis would be. So you need to find those principal, means you need to find principal axes, and you know what are principal axes about which the mass will be uniformly distributed. So which 2 axes are possible? So 2 axes are given. For this these are given and these are given and these are given. So we need to verify that which are the principal axes. So see, for this figure, if you rotate along this axis, it will give you symmetry. So that's why you have this as principal axis. Now along this, if you rotate, it will again give you symmetry along both axes. So this is also symmetrical. Now in this, if you rotate along this axis, so this will give you symmetry along this axis also. So that's why this is also valid. And when you rotate along this axis, it will give you symmetry along this axis also. But there are 2 axes, are this one and this 2. So when you rotate this figure along this axis, so you will get symmetry only around this but not this. And same if you rotate this figure along this axis this way, then this will give you symmetry along this axis only but not this. So these 2 axes are not principal axes, but these 2 are. So answer will be P and Q only. Let's see one more question. A plate of mass m, capital M, and shape as a coordinate of an ellipse is lying in the xy plane as shown in the figure. The value of Ixy is. So this is the component of moment of inertia tensor. So we need to find this. So you know for this what you need? Ixy, you need mi, xi, yi. So to find the mass, you must know the density. So here it is a 2D plane, so it is mass per unit area. So total mass, if the mass of this quadrant is m, then total mass of ellipse will be 4m divided by pi ab is area of ellipse. This is your mass per unit area. So you can find the mass of this particular area. So this is mass per unit area multiplied dx dy will give you a small mi and xy as it is. So this is your formula. I just place it in place of mi. We have write it sigma and dx dy. So sigma dx dy will give you small mass m multiplied by xy. So this integration will give you your Ixy component. Now you just need to solve this integral. So see, we can place the value of sigma. This is constant. This will be 4m by pi ab. Now take the limits x for dx and y for dy. Now see, these here x and y are depending on each other because this is ellipse. So limits of x, we take the independent variable as x. So x is going from 0 to a, and then y is depending on x. So y will be taken upon from here. This is the equation of the ellipse. Y will be under root 1 minus x square by a square and b. So y will go 0 to this. When you will substitute x, it will give you this value. Now to solve this limit first, it will be y square by 2. It will give you 1 minus x square by a square. Now multiply with x and integrate this with respect to x now. So you know how to solve these integrations. I already told you in the vector analysis when we discussed in the mathematical physics. So you can solve these. So this is a simple integration, x square by 2, x4 by 2. Put the limits a0 and the answer will be minus MAB divided by 2 pi. So this will be your component IXY. Let's see one more question. Find the moment of inertia tensor of the semicircular disk, mass m and radius r, origin at the center of the disk. So we need to find along this center. We need to find the actually the tensor, means we need to find the complete matrix. So we can write it directly. You know, this is the symmetrical axis, and this will form a disk when you rotate along this z axis. And you know, along the z axis, it is will be mr square by 2 for the central axis, and mr square by 4 along this, mr square by along y axis. So you already know this, but so let's verify by the result we are getting for the tensor if we are getting the same result or not. So see here, we know that this figure is lying in the xy plane, so z component will be 0. So from the formula for the IXY, these will be 0, means anything which is involving z will be 0, IXZ, IZY, IYZ, IZY. So all these components will be 0 as z is 0. And the mass per unit area density will be, this total mass will be 2m, the mass of the half disk is m, then complete will be 2m divided by pi r square. So this will give you mass density. Now you know how to find the IXY, IYX. So using this formula again, same as we did here. Sigma xy. Now we will take in the polar coordinates this thing. So you can represent xy coordinates in polar coordinates, means area element will be given by r dr d theta, and it will be sigma r dr d theta will give you small mass. Now xy also can be written in terms of polar coordinates. X is nothing but, if this is your r, then it will be r cos theta, and this is theta angle, r cos theta, and y will be r sin theta. Just substitute here and put the limit for r 0 to r, and theta is going from 0 to pi. So this will give you, means it will be 1 upon 2 sine 2 theta, and you know, for the this limit pi 0, sine 2 theta will means after solving this limit you will get 0. Try to solve this, you will get 0 definitely. Now let's find the IXX. So you know what the formula for IXX, that is m y square plus z square, and m is sigma r dr d theta again. So that is the same thing as we did here. Now what we will do, we will just integrate. Right in place of y, r sin theta, and z is 0. So r sin theta will give you r square sin square theta. So r square multiplied this r will give you r cube, and sin square theta d theta. This integral, you know, if it is sin square theta cos square theta here, and limit is 0 to pi, so whatever there is, just take the half of that. That will be the answer. That will be pi by 2 here, and it will be r4 by 4. It will give you r4 by 4. So you can just multiply them and solve this. This is the simple mathematics. It will give you mr square by 4 IXX. And similarly you can do for the IYY. There you will have the formula sigma x square plus z square, and you will write in place of x, that is x square means r square cos square theta, and you can solve that again. Cos square theta will give you pi by 2, and you can get the result same as for the IXX, that is IYY will be mr square by 4. Now there is third component, that is IZZ. In that the formula will be sigma x square plus y square. Then what you will get, at that time you will substitute in place of x r cos theta and y r sin theta. So it will give you sin square theta cos square theta 1, and you will get r square common, and you can solve this way, means you will get this result. R dr d theta multiplied with r square will give you r cube dr d theta, and limits will be 0 to r, it will give you r4 by 4. So r square will cancel out 1 r square, so it will give you 2 in the denominator, mr square by 2. So you can solve this, it will give you mr square by 2. Limit is 0 to capital R. Now see, you can write the matrix or the moment of inertia tensor. This is IZZ, IXX, and IYY, and other components are 0. So off diagonal elements are 0, but you are getting only on the diagonal elements. And why is that? Because the principal axes are along the XY. So when they are XY along the, means mass distributed symmetrically around the XY, we already know the moment of inertia exists only on those axes, means you will get off diagonal elements as 0. So remember this result always. Let's see one more question. This figure is given. This is some square figure on which the mass is distributed, and these 4 masses are also in the above it. Here also small mass m. So question is, EFGH is a thin square plate of a uniform density sigma. This is the mass density, and side 4a. 4 point masses each of a small mass small m are placed on the plate as shown in the figure in the moment of inertia tensor of this composite system. So these are given like that. Now in the moment of inertia tensor of this composite system, which option will be correct? Only IXY will be 0, only IXZ and IYZ are 0, all the product of inertia terms are 0, or none of the product of inertia term is 0. So see, this term, none of the product terms is 0. This is wrong. Why? Because this is lying in the XY plane, so all the z involving x, z, y, z, zx, so all will be 0. So but it's not, means this is wrong and this is also wrong, because only ix, z and yz are 0, but other terms are also 0, zx and zy are also 0, and this is also wrong. So basically I can tell you directly here that C will be correct, because these three are wrong, but we can check it. Means directly we can see that this is symmetrical axis. Means what will be the symmetrical axis for this, or the principal axis is, this mass is distributed symmetrically around the xy, so it is symmetrical around the x, it is symmetrical around the y, and if you take the z also, it was symmetrical around the z also, this whole mass. Then I already told you this result. If the mass is symmetrically distributed along the x, y and z, then all the off diagonal elements are 0. So here also we can directly say that all the off diagonal elements we will get will be 0. So only the C option, all the product of inertia terms are 0. So this will be correct directly. In this case, x, y, z axis have the symmetrical distribution of the mass and rotation. So product of inertia will be 0. Means all the off diagonal terms are 0. So this is a result you must remember, that if the mass is distributed symmetrically around the x, y and z axis, then off diagonal elements will be 0 always. Let's see one more question. Two masses mh. This question also can be done directly by seeing. So two masses m each are placed at points AA and -A. So m mass is placed at AA and -A, and the mass 2m is placed at A minus A and -AA. So 2m is placed here, and m is placed here and here. The principal moment of inertia system are. So we need to find the principal moment of inertia. So this these two masses, means if you take how you can find the principal axis. First check for the x. See, this here is m and 2m, and here is 2m. So this is not distributed symmetrically around the x or along the y, but we can see these axes. This axis here is so this is lying on the axis, and this here is 2m, here is 2m. So this mass is symmetrically distributed around this axis, and again you can take this axis. So this is 2m on the same axis, but this m is symmetrically distributed around this axis. So these two axes are your principal axes. So you can find the moment of inertia along these, and that will be your principal moment of inertia, because these are principal axes. So for this first axis, mass lying on the axis will not count. You will take this one and this distance square, this mass into this distance square, and sum will give you moment of inertia. So this distance will be a and minus it will give you a square plus a square will give you under root 2a, this distance. So 2m multiply under root 2a square plus 2m under root 2a square, this will give you moment of inertia along this axis. This will be 8 m a square. Now the moment of inertia along this axis will be, so it is m, the distance square under root 2a square, and m multiply this through distance square, it will give you 4 ma square. So this will be your moment of inertia along the principal axis, or this is your principal moment of inertia. Let's see one more question. Moment of inertia of a rigid body is given by, so this is moment of inertia tensor is given. We need to find the moment of inertia about an axis. So axis is given. So as we did this question already, so you need to find the moment of inertia along any particular axis. Just put that axis. Means consider this as some column vector. Not this. Means they will give you like this, but you will take it as column vector. And take the transpose. Transpose will be this right here, and that column vector right here. Again transpose and the same vector, and this will be your tensor which is given. Solving this will give you your moment of inertia along that axis. Let's see the last question for today. A uniform circular disc on the xy plane with its center at origin has moment of inertia I naught about the x-axis if the disc is set at rotation about the origin with omega equal to omega naught j cap and k cap. Direction of its angular momentum is. So we need to find the direction of angular momentum. So we know the formula for angular momentum, that is I tensor omega. So first write the I tensor. So this is a uniform circular disc. So the principal axis will be x, y and z. So off diagonal elements are 0, and diagonal elements will give you moment of inertia along those axes. So it will be I naught, and 2 I naught. So this will be your moment of inertia tensor. Now L will be this, and omega is given, that is omega naught j cap, omega naught k cap. So it is omega naught. Now multiplying these, it will give you 0, I naught omega, 2 I naught omega, and you can write it in terms of vector I naught omega and j cap plus 2 k cap. So this is the direction of angular momentum, and this is the direction given for the angular velocity. So that's how you can find, or you can solve the questions. So we'll discuss some more questions in the next lecture. Then we'll discuss about the Euler's angle, and there will be 3 or 4 lectures more. Then that's all for the classical mechanics or the classical physics. So thank you everyone. We'll meet you in the next lecture.